Welcome to the Sleepy Science Facts. It's a gentle evening, and as you settle in, I invite you to find a comfortable position. Allow your body to soften and your mind to relax. If you enjoy our soothing explorations, consider liking and subscribing as we drift into the quiet wonders of science together. Electrons play a vital role in the flow of electricity. These tiny particles carry a negative electric charge and are always at the heart of electrical activity. Invisible to the eye, electrons exist in the outer layers of atoms, moving freely in certain materials, particularly metals. It is within these conductive materials that their behavior becomes significant. Over time, the way electrons interact and move can remain stable, contributing to what we understand as electrical conductivity. This stability allows electrons to flow effortlessly, facilitating a constant stream of energy. As they navigate through the atomic structure of these materials, they create a pathway for electricity to travel, which is essential for many electrical systems. With every gentle movement, electrons continue their quiet dance, forever establishing the foundation of electrical flow, guiding the energy across vast distances, silently performing their essential role. From here, we can delve deeper into their existence and discover more about their delicate interactions. Certain natural phenomena, such as El Niño and La Niña, weave their influence into the fabric of our weather. These changes occur in ocean temperatures, and they ripple through the atmosphere, subtly shifting wind patterns and precipitation. During an El Niño event, warmer ocean waters can create milder winters in some regions, leading to a decreased need for heating. In contrast, La Niña may bring about cooler ocean temperatures, often resulting in colder winters, stirring the need for warmth and increased energy consumption. As these patterns unfold, they affect the climate for extended periods. The long-term interactions between ocean and atmosphere create a complex system where the climate can gradually shift, altering how energy is consumed over time. The gentle ebb and flow of these natural cycles quietly remind us of the interconnectedness of the Earth's systems, whether it be in the warmth of a summer day or the chill of winter nights. The electric pulse of energy remains in harmony with the ever-changing rhythms of nature, existing in a balance that invites further exploration. Inside batteries, there exists a phenomenon known as internal resistance. This characteristic plays a crucial role in how efficiently a battery can store and deliver energy. As the battery ages, this internal resistance gradually increases, much like the subtle wear of time upon any object, affecting the flow of electricity. The resistance tends to create a barrier, gently diminishing the battery's ability to provide a consistent power output. This change can lead to longer charging times as the energy struggles to move freely through the increased resistance. Consequently, you may notice a shift in performance. The once lively energy may feel subdued as it relates to the system it supplies. The interplay of charge and discharge cycles is delicately impacted by this internal structure, highlighting the intricate balance within the battery itself. Each cell contains materials that undergo changes, gradually influencing the overall efficiency. Over time, these shifts remind us of the natural processes at work, quietly guiding us toward a deeper understanding of energy dynamics while inviting observations of the ever-evolving landscape of electrical systems. At the boundary where two different materials meet, a gentle interaction occurs, known as electrical double layers. This phenomenon creates a region where an accumulation of charges begins to form, quietly influencing the behavior of electricity and ions in nearby fluids. When materials come together, their distinct properties interact, leading to the establishment of these layers. In essence, one side may exhibit a positive charge while the other subtly counters it with a negative charge. This delicate balance affects the flow of ions and electricity across this interface, creating a bridge of sorts that permits movement while also introducing a gentle resistance. As ions drift through the fluid, their paths are subtly guided by the presence of these double layers, contributing to the overall dynamics of the system. Observed on a microscopic scale, these layers create an intricate dance of charges that can influence the efficiency of electrical conduction. As the layers build and reshape, they embody a quiet complexity, reminding us of the unceasing interactions that define the essence of electricity. With every shift and change, the layers continue their subtle work, influencing the very nature of how energy flows within these structures. When light gently touches certain materials, a remarkable interaction unfolds, known as the photoelectric effect. In this tranquil moment, the energy carried by light waves can free electrons from the surface of these materials. As light photons strike, they impart their energy to the electrons, allowing them to escape and flow away. This process occurs with specific materials that are finely tuned to respond to light in such a way. As the photons engage, they nurture the electrons, releasing them into their surroundings. This release creates a small but significant current, hinting at the hidden energies that lie within these substances. Over time, the continuous exposure to light can lead to a steady stream of electrons moving through the material, showcasing a consistent response to illumination. The photoelectric effect reminds us of the soft interplay between light and matter, revealing a quiet transformation of light into electricity. As electrons drift away, they carry with them the potential for new connections, embodying the serene dance of energy interaction that continues to unfold in the shadows of observation. Within the realm of pressurized electrical systems, a serene balance exists, governed by carefully defined pressure limits. These parameters are not merely numbers, but rather they nurture stability and safety in the system. As the pressurized environment maintains its designated range, a sense of calm resilience unfolds within the materials and components. Over time, as the system operates steadily within these limits, a natural reliability develops. The materials adapt to the consistent conditions, enhancing their durability and performance. This long-term harmony minimizes the potential for pressure failures, creating a peaceful rhythm of operation that mirrors the predictable cycles of nature. With each passing moment of steady pressure, the components grow accustomed to their surroundings. This gentle interaction fosters an environment in which risks are reduced, allowing the system to function quietly and efficiently. The stable conditions offer a reassuring backdrop, hinting at the enduring strength and dependability that arise from this harmonious balance, ready to continue its calm presence in a world of energy. Hydroelectric plants, nestled along flowing rivers, find themselves in a gentle dance with nature, influenced by the patterns of annual rainfall. Each year, as rain nurtures the land, it flows into rivers and streams, gathering in reservoirs. This consistent cycle creates an ebb and flow of water availability, rising and falling with the seasons. During periods of plentiful rainfall, the reservoirs fill and the power generation potential grows. Water cascades down, embracing the turbines, converting the kinetic energy of flowing water into electricity. As the seasons shift, the rhythm of rainfall may fluctuate, allowing for variations in water levels. This connection between rain and energy production exemplifies a quiet reliability, where nature's bounty directly affects the flow of electricity. Over time, adapting to these cycles enhances the stability of the system. The components within the hydroelectric plant harmonize with the natural rhythms, creating an ongoing balance that nurtures consistent energy production. This tranquil interplay continues, a soft reminder of the natural world's influence, ever moving and ready to sustain its gentle current. Electric power, measured in watts, emerges from a delicate interplay of voltage and current. This relationship creates a steady balance that influences energy dynamics in a harmonious way. As voltage rises and current flows, the resulting power output reflects how they interact in a linear fashion. Under stable conditions, this linear connection remains consistent, providing a foundation for understanding energy flow. Over time, the patterns of power usage can gently shift, often in response to subtle changes in infrastructure and advancements in technology. As regions grow and adapt, the average energy consumption may rise or fall, reflecting evolving patterns of life. Population density might also play a role, with more people tending to demand more energy. Yet throughout these fluctuations, the essential connection between voltage and current persists. This enduring relationship assures that as circumstances change, the fundamental nature of electrical power continues to flow with ease, creating a steady undercurrent in the world of energy. Quietly, these dynamics remain in place, ready to respond to the natural rhythms of a changing environment. Every conductor, regardless of its type, possesses a specific maximum temperature it can endure. This critical temperature marks the threshold known as the melting point of the material. Approaching this point, the conductor becomes vulnerable, and its ability to conduct electricity may begin to diminish. Each molecule within the conductor remains in a delicate balance, interacting in a way that ensures effective conductivity. As the temperature rises close to the melting point, the organized arrangement of atoms starts to shift. They gain energy and move more vigorously, disrupting the regular flow that allows electrical currents to pass smoothly. If the material exceeds this limit, degradation may occur, potentially leading to a loss of functionality. This intrinsic characteristic is inherent to the physical properties of the conductor, forming a core aspect of its identity. Understanding these limits allows a sense of awareness of how materials interact with changes in their environment. In this way, the quiet resilience of conductors stays present, ready to respond to unfolding energy needs while remaining within their protective boundaries. The permittivity of a dielectric material serves as a fundamental property that defines its interaction with electric fields. This stability is notable as it remains largely unchanged under regular conditions of temperature and pressure. It quietly holds the key to how the electric field interacts with the medium itself. Within the material, atoms and molecules align themselves in a specific way, creating an environment that determines the material's response to electrical forces. Under typical circumstances, this interaction displays consistency, allowing for predictable behavior. However, variations may arise when the material encounters extreme conditions, like significant increases in temperature or pressure. Changes can also occur when exposed to different frequencies of the electric field, altering the way the space surrounding the material responds. Despite these potential fluctuations, the inherent nature of permittivity remains mostly stable in familiar environments, allowing the dielectric material to maintain its unique characteristics. The quiet presence of this property contributes to a deep understanding of the physical world, where the gentle interplay of electric fields and materials continues, patiently awaiting further exploration. Pressure softly influences the conductivity of various materials, most notably semiconductors. Within these special substances, the arrangement of atoms plays a crucial role in their ability to conduct electricity. As pressure gradually increases, these atoms shift ever so slightly. This delicate rearrangement can lead to changes in the material's conductivity. When the atoms settle into a new configuration, the pathways for electrical flow can either be enhanced or diminished. In some cases, this increase in pressure may allow electrons to move more freely through the material, boosting its conductivity. In other instances, the increased pressure may create barriers that hinder that flow, reducing overall conductivity. This gentle dance of atoms can notably affect how well electronic devices perform, evolving subtly over time as pressure ebbs and flows. In this quiet realm of semiconductors, each change, no matter how small, builds upon the last, shaping the behavior of electricity within. The serene interplay of pressure and conductivity continues, always present, always influencing, waiting for the next moment of change. Subtle shifts in climate can gradually alter the availability of hydroelectric power. As rainfall patterns change, the flow of water in rivers often transforms alongside them. This delicate balance impacts the movement of water through dams and other hydroelectric systems over long periods. Where once there might have been abundant rain, steady streams may dwindle, leading to a reduction in water flow. Conversely, changes may also bring periods of increased rainfall, creating a surge in water levels. Each tiny shift influences the overall capacity for energy generation, weaving together a long-term narrative of supply and demand. As these elements of nature continue to evolve, the interconnectedness of water flow and energy production reveals itself with quiet clarity. The rivers, ever flowing, adapt to these new rhythms, responding gently to the slow crescendos and diminuendos of rainfall. In this tranquil cycle, the essence of hydroelectric power remains intricately linked to the dance of the elements, poised for whatever future changes may arise. A single electron carries an electric charge of approximately -1.6 x 10, circumflex 19 coulombs. This value stands unwavering, a constant presence in the world of physics. Each electron, with its defined charge, plays a key role in shaping the interactions that occur within various materials. This stability is essential for understanding how electricity flows. As electrons move through conductive materials, they act as messengers of energy, conveying electrical forces from one point to another. In insulators, their absence creates a different dynamic, allowing for the study of how charges can build up on surfaces instead of flowing freely. Day after day, this consistent charge remains a foundation upon which deeper insights into the behaviors of atoms and particles can be built. Interactions between those charges lead to the creation of forces that bind materials together or enable the movement of energy. With each passing moment, the world continues to unfold around these tiny charged particles, their influence quietly reverberating through the fabric of existence, ever steady and ready to shape the dance of energy that fills our surroundings. Transmission lines consist of metal strands, intricately twisted together, creating a structure that enhances both strength and conductivity. This careful design allows the lines to carry energy efficiently, ensuring that electrical signals can travel long distances with minimal loss. Over time, these lines experience various environmental factors, which may lead to signs of wear. They endure the gentle embrace of the wind, the steady pressure of rain, and sometimes the caress of temperature fluctuations. Despite these stresses, the robust construction helps them endure, providing a reliable pathway for energy to flow. Though wear may appear as part of their journey, these lines are built to withstand the test of time. Their metallic nature, allows them to maintain a reliable connection, even in the face of changes. This resilience is a quiet testament to the harmony of materials and design as they continue to carry their charges forward, intertwining with the pulse of electricity that surrounds them. Each strand contributes to an ongoing story of energy, ever present and ready to move into the next moment. Understanding the principles of energy conservation evolves gently across generations. Information about climate change and its effects slowly seeps into public knowledge, creating a gradual awareness that nurtures a sense of responsibility. Education plays a pivotal role in this process, allowing the intricate relationships between energy use and environmental health to come into focus. As awareness grows, more individuals begin to adopt energy-saving practices. Small changes in daily habits can accumulate into meaningful reductions in electricity usage over time. Simple actions, such as turning off lights when not in use, choosing energy-efficient appliances, or using natural light when possible, become part of the rhythm of life. Each mindful choice contributes to a larger cultural shift, reflecting a deeper understanding of resources and their impacts. This evolving mindset fosters a collective commitment to a sustainable future. Such shifts may unfold quietly, but they weave together a tapestry of change that spans years, enhancing the balance between human activity and the preservation of the surrounding environment. Embracing this understanding allows for the continuation of harmony. Within the world of batteries, the relationship between electricity and thermal energy is a delicate balance, one that functions in harmony under normal conditions. However, when temperatures rise, this balance can shift. In these moments of increased heat, the internal resistance of the battery may decrease, allowing more electricity to flow through the system. This influx of electrical energy further contributes to the rise in temperature, a phenomenon known as thermal runaway. As the temperature continues to climb, chemical reactions within the battery can become more vigorous, producing even more heat. This escalating cycle may lead to the battery reaching a critical point. If the thermal energy exceeds safe limits, it creates a significant risk of fire or explosion, demonstrating the powerful interplay between electricity and heat within these compact systems. Understanding this dynamic provides insight into the importance of temperature regulation in battery design. Keeping this balance steady ensures a safer, more reliable energy storage solution. Such awareness opens pathways for continued discussion, highlighting the intricate nature of energy systems that operate quietly in the background. Inductive charging systems operate on a principle that allows energy to transfer efficiently without any direct contact between the components. This method involves the use of magnetic fields, which can create a pathway for electricity over short distances. When the transmitting coil and receiving coil align appropriately, energy flows smoothly, providing a steady source of power. The design of these systems supports a consistent transfer of energy across extended periods, ensuring that devices remain charged and ready for use. The precision required for this alignment is notable, as even slight misalignments can affect performance. However, when positioned correctly, the efficiency of energy transfer remains high, contributing to a stable operational state. These systems highlight the beauty of energy transfer, seamlessly connecting without the need for physical links. With each interaction, energy moves fluidly, continuing its journey. This ongoing process reinforces the underlying principles of electromagnetic interactions, inviting contemplation and allowing a sense of tranquility to settle. As this exploration unfolds, an appreciation for the quiet mechanics of energy begins to take shape. Within electrical outlets, metal contacts are thoughtfully designed and positioned to facilitate a secure connection with plugs. This arrangement is crucial as it allows for a firm grip, ensuring that the connection remains intact during use. The metals chosen for these contacts often possess high conductivity, enabling electricity to flow freely and efficiently once the plug is inserted. The design accounts for the physical demands of regular use, as plugs may be inserted and removed repeatedly over time. Each insertion creates a moment in which the contacts meet, establishing a reliable pathway for energy. With each connection, the metal contacts work to create stability, effectively accommodating the wear and tear that occurs with countless cycles. This repeated interaction contributes to an enduring relationship between the outlet and the plug, where the essential task of energy transfer occurs smoothly and without disruption. Each moment of contact carries with it a sense of continuity, connecting the inherent properties of electrical components with the quiet flow of energy as it journeys onwards. In this persistent exchange, the fundamental nature of electricity and materials reveals itself softly and patiently. Pricing structures for electricity reflect the intricate nature of supply and demand in an ever-evolving landscape. Over time, utilities observe patterns in energy consumption, noting when usage peaks and when it ebbs, creating a rhythm that informs their decisions. To manage this ebb and flow, adjustments to rates can be made, often aimed at encouraging off-peak consumption. This approach helps to balance the load on the electrical grid, allowing for more efficient use of resources. Changes are made gradually, ensuring that the system adapts smoothly without causing disruption. By adjusting prices to reflect the varying demand throughout the day and week, these utilities aim to create harmony in energy distribution. This steady evolution of pricing mirrors the natural fluctuations in energy needs, ensuring that electricity remains available when it is most required. Each small shift contributes to the larger framework of energy management, fostering a sense of equilibrium in the relationship between consumption and supply. Such subtleties continue to unfold quietly, inviting a deeper understanding of how energy flows through our interconnected systems. The flow of current through a wire is governed by a key concept known as ampacity, which defines the maximum amount of electrical current a particular wire can handle safely. This limit is determined by various factors, including the wire's gauge, the material it is made from, and the temperature at which it operates. Each wire is designed with specific properties that dictate its performance under different conditions. When the current flowing through a wire exceeds its ampacity, it begins to generate heat. This heat is a natural byproduct of electricity moving through a conductor, but becomes a concern when it surpasses safe levels. If the wire gets too hot, it can lead to insulation breakdown, which compromises the protective layers surrounding the wire. In extreme cases, overheating can result in dangerous situations, such as the risk of fire. Therefore, understanding ampacity is crucial for maintaining safety and ensuring that electrical systems function smoothly. Keeping current within safe limits creates a balance, allowing the flow of electricity to proceed effectively without risking damage or danger. Such considerations form an essential part of the underlying structure of electrical systems, where every element works together to ensure harmony and safety. As this intricate interplay unfolds, it quietly sustains the pathways through which electricity journeys, deepening our connection to the world around us. The structure of electrical grids is in a state of gradual transformation, influenced by the increasing presence of renewable energy sources. This shift alters the very fabric of how electricity flows through the system. Wind, solar, and other sustainable forms of energy introduce new dynamics, which require time to fully integrate. The balance between traditional and renewable energy sources doesn't happen overnight. Rather, it unfolds slowly, with each element adjusting to coexist harmoniously. As renewable energy becomes more prevalent, the grid must adapt its composition, accommodating the variable nature of these sources. The voltage, frequency, and stability of the electricity delivered can change as the proportion of renewables shifts. This delicate equilibrium affects not only how energy is produced, but also how it is distributed and consumed. Communities find themselves in a gradual learning process, adjusting their patterns of energy use to align with these new distributions. Routine habits transform gently, reflecting a deeper understanding of the ebbs and flows of energy availability. It is a time of transition where the rhythms of electricity create a dance between past practices and future possibilities. This ongoing evolution embodies a quiet promise of balance, stretching into the horizon as nature and technology weave together in new ways. Certain materials possess a fascinating ability to retain residual electricity even after the power has been turned off. This phenomenon reflects the stability of stored electrical energy, rooted deeply in the dielectric properties of those materials. Dielectrics can store electrical energy in the form of an electric field, a characteristic that lingers in the environment around them. When an electrical charge passes through these materials, they become polarized, creating a temporary change in their internal structure. This change can maintain an electric field for a period, even when the external power source is removed. It is a gentle reminder of how energy can reside quietly within a physical structure, waiting patiently until it is needed again. The degree to which this residual electricity lingers depends on various factors, such as the material's composition, thickness, and temperature. The quiet dance of charges within these substances unfolds over time, revealing their inherent stability. As they release the stored energy, it does so softly, shaping the manner in which electrical signals might behave in subsequent interactions. Each moment embodies the intricate balance and patience of energy storage, an ever-present reminder of the elegant complexities hidden within materials. The story continues with the gentle hum of potential just beneath the surface, ready to be explored further. The electrostatic force at play among charged particles creates a subtle but impactful potential energy difference. This interplay allows for a gradual buildup of energy, setting the stage for the flow of electricity. When particles acquire an electric charge, they interact with each other through forces that either attract or repel them. These forces bring about distinctions in energy levels, leading to regions of higher and lower potential. As these differences exist, there emerges a pathway for energy to migrate, forming the essence of electricity. Over time, as particles move in response to these forces, a current begins to flow. This flow transmits energy along power lines, where it can travel vast distances, all while oscillating gently between poles of positive and negative charges. Each strand of electricity carries with it the potential energy stored in those differences, reflecting a consistent dance between attraction and repulsion. The continuous movement creates a rhythm, influencing the environment through the ease or resistance encountered, ebbing and flowing as it travels. It's a calm exploration of forces existing in a state of balance, and the potential for more energy exchange remains ever present, quietly inviting the listener to delve deeper into the wonders that lie within this graceful system. Electric currents navigate through circuits, which serve as designated pathways, allowing electricity to travel smoothly and systematically. Within these circuits, components such as resistors and capacitors play essential roles. Resistors possess properties that limit the flow of electricity, creating a gentle resistance that modulates the current's intensity. This regulation contributes to the balance within the circuit, ensuring that energy flows steadily without overwhelming any part of the system. Capacitors, on the other hand, store energy for brief moments. They gather electric charge and release it when needed, acting as small reservoirs within the circuit. Their ability to retain and release energy adds another layer of rhythm to the flow of electricity. The characteristics of these components remain stable over time, allowing circuits to function predictably under various conditions. As electricity travels through these interconnected parts, it experiences a continuous dance of movement and energy exchange. The interplay among these components creates a harmonious environment where electric currents can thrive, quietly reinforcing the delicate balance that governs their behavior. This tranquility invites deeper contemplation of the intricate connections within, sustaining a gentle flow of energy that resonates softly through the paths they traverse, open and ready for further exploration. Electric field strength exists within a defined range, a gentle boundary that materials can withstand without experiencing ionization. This threshold is a delicate balance, reflecting the maximum intensity of the electric field that can be applied safely. When this limit is respected, materials maintain their integrity, allowing for a stable flow of energy. However, as the electric field strength approaches its maximum capacity, there exists the potential for change. If the strength surpasses this critical point, it can lead to ionization, a phenomenon where electrons are stripped from atoms. This process can result in unwanted discharge, disrupting the peaceful flow within a circuit. Components may suffer damage, altering their ability to function as intended. This inherent limitation ensures that the environment within circuits remains harmonious. The materials respond to the electric field in predictable ways, quietly reinforcing the need for balance. Understanding these parameters allows for a serene interplay of forces, where the energy can continue to flow smoothly. Each movement is measured, with safety woven into the very fabric of electrical behavior, inviting a gentle exploration of its boundaries while remaining calm and steady. The rise of electric vehicles introduces a gradual transformation in how electricity is understood and consumed. Each vehicle relies on stored energy, quietly drawing power from charging stations to replenish its battery. As more electric vehicles integrate into everyday life, the gentle hum of increased demand begins to echo softly in the landscape of energy consumption. Charging stations, once sparse, evolve into more prevalent structures, quietly accommodating this shift. Over time, this expansion creates a network of access points, fostering a new rhythm in energy usage. The changing dynamics remind us of the interaction between technology and energy resources, weaving a quiet tapestry of connection. This evolution unfolds slowly, marking a transition that can stretch over decades. Awareness of electricity morphs into a deeper understanding of its role in sustaining movement. The intertwining of electric vehicles and energy consumption establishes a lasting influence on infrastructure, reshaping perceptions in subtle yet profound ways. Each added vehicle contributes to a larger narrative, encouraging a thoughtful exploration of energy's journey and allowing these ideas to intertwine with one another. The phenomenon of electric field-induced polarization unfolds within non-conductive materials when exposed to an electric field. In this state, the internal structure of these materials undergoes a subtle rearrangement. Tiny dipoles within the material align themselves, responding to the field that surrounds them. This alignment creates a momentary condition in which the material may exhibit a degree of conductivity, shifting from its usual state of isolation. As this process occurs, the molecules adjust to the influence of the electric field, revealing a delicate interplay of forces at work. Capacitors, integral parts of electronic systems, rely on this property to store and release energy, embodying the essence of charged interaction. The same principle finds its way into sensors, enabling them to detect and respond to changes in their environment. Over time, these effects weave themselves into the fabric of electronic behavior, influencing how energy is manipulated within devices. The temporary transformation within these materials is consistent yet fleeting, a quiet reminder of the remarkable adaptability that exists at the microscopic level. The gentle shifts in electric fields continue, creating experiences that are both serene and intricate. Electricity, when flowing through a conductor, gives rise to magnetic fields, which are invisible yet profound influences within the realm of physics. These fields emerge as a natural consequence of moving electric charges. As the charges travel along their paths, their motion creates a surrounding magnetic field, intertwining the two forms of energy in a harmonious dance. The nature of these magnetic fields is such that they interact with other charged particles, guiding their movement in subtle and complex ways. Within this interaction, a sense of balance exists, resulting in a push and pull that is quietly perceptible. Over time, this interplay helps to define the behavior of various systems, establishing a foundational relationship between electricity and magnetism. Within these magnetic fields, energy and motion coalesce, leading to a variety of effects that contribute to the stability and dynamics of different physical materials. As electric currents continue to flow, magnetic fields persist, gently enveloping the space around them, creating a tranquil yet essential undercurrent in the fabric of nature. This connection between electricity and magnetism remains a constant, quietly influencing the environment, ready to unfold further in its intricate and serene journey. Electricity consumption reveals a natural rhythm that aligns closely with the seasons. As winter arrives, the colder temperatures invite an increase in energy usage, driven by the need for heating. In homes, warmth envelops spaces, creating a safe haven against the chill of the outside world. The demand for electric heating rises, bringing with it a glow of lights and warmth that permeates through the winter evenings. When summer unfolds, the energy landscape shifts once again. Rising temperatures usher in a new pattern of consumption, often marked by the use of cooling systems. Air conditioners hum to life, refreshing spaces and providing relief from the heat. Operating in tandem with fans and other cooling methods, these systems create a comforting environment during the long, warm days. This cyclical dance of electricity consumption reflects the rhythms of nature and the changing climate. Each season brings its own patterns and needs, harmonizing with the flow of energy, cycling through periods of higher and lower usage. This intrinsic connection to the seasons quietly underlines the gentle ebb and flow of electricity, awaiting the next seasonal shift. The conductivity of a substance plays a gentle yet important role in the flow of electricity. This property measures how readily electrical current can move through materials. In metals, a fascinating relationship exists with temperature. As the temperature rises, the atomic structure within these metals experiences an increase in vibration. At higher temperatures, atoms shake and jostle more energetically, creating obstacles for the flowing electrical charge. This increase in atomic activity causes a subtle decline in conductivity. The harmonious movement of electrons becomes hindered by the bustling atoms around them, slowing their path through the metal. As a result, the smooth passage of electricity is gently disrupted. Conversely, when temperatures cool, atomic vibrations decrease. The atoms settle into a more stable state, offering a clearer path for electricity to travel. This change creates an environment where conductivity can increase, allowing electrical currents to flow more freely. Such a responsive nature reflects how conductivity weaves through the fabric of metals, quietly adapting to the changes in temperature. Each shift in warmth brings about a natural ebb and flow in the ability of these substances to conduct electricity, creating a calm and continuous cycle of behavior that patiently awaits the next change. The demand for electricity is a dynamic aspect of the physical world, shifting gently over time. This change often occurs gradually, emerging from patterns in population growth and the evolution of technology. As more people inhabit a region, they bring with them a subtle increase in the need for electrical energy. Houses fill with devices and appliances, which contribute to the slow rise in consumption. Over the years, these patterns can expand beyond just numbers of people. Technological advancements introduce new forms of energy use. When innovation occurs, such as the adoption of electronic devices or renewable energy systems, the way energy is consumed can shift significantly. Each small addition builds upon the last, resulting in a gradual cumulative effect that alters overall demand. Generation strategies quietly adapt to these changes over decades. Energy sources may shift as utilities respond to growing or diminishing needs. This multifaceted interplay of consumption fosters a gentle transformation of the energy landscape, which flows and ebbs in sync with the world around it. The process remains an ongoing cycle, ever responsive to the natural progression of society, patiently guiding the way forward. In piezoelectric materials, a delicate balance exists between the applied stress and the resulting electrical charge. Each material has a threshold stress, a precise point where it begins to generate electricity in response to deformation. This transformation occurs gently as the internal structure of the material responds to the forces being applied. As stress increases, the tiny crystalline components of the piezoelectric material rearrange slightly, creating an electrical charge. However, once this threshold is surpassed, the material faces a risk of permanent deformation. The internal lattice structure can change irrevocably, leading to a loss of those valuable piezoelectric properties. The material may no longer produce electricity efficiently as its once orderly arrangement becomes disrupted. This threshold serves as a silent reminder of the fine line piezoelectric materials walk. Each application of force carries with it the potential for unique electrical generation, while also holding the possibility of altering the material's fundamental capabilities. This gentle interplay of stress and structure reveals the nuanced nature of the physical world, echoing the harmony present in so many systems. The process unfolds steadily, remaining a constant cycle, quietly waiting for the next application of energy. Electrical properties of materials are not static. They can evolve gradually as time passes. This transformation occurs subtly, often influenced by environmental conditions. Take copper, for example, a metal known for its excellent conductivity. When exposed to moisture and air over years, copper can begin to corrode. This slow deterioration alters its ability to carry electrical current effectively. The surface of copper reacts with oxygen and moisture, gradually forming a layer of copper oxide. This layer serves as a barrier, interrupting the flow of electricity and resulting in increased resistance. Such changes are often imperceptible at first, yet they accumulate, leading to a substantial impact on the material's performance. This aging process in materials reflects a deeper truth about the physical world. It shows how even the most reliable substances can evolve, affected by their surroundings and the passage of time. Each tiny shift resonates through the material, whispering of its aging journey. Understanding these changes carries a sense of calm, reminding us of the interconnectedness and continuity present in nature. With each moment, the story unfolds quietly, waiting patiently to reveal more in the gentle embrace of time. The sun moves through a cycle that spans roughly 11 years, known as the solar cycle. This cycle is not just a passage of time, it influences the way the sun emits energy. During certain phases of this cycle, the sun becomes more active, producing higher levels of solar radiation. This heightened activity can create an increase in the energy available to solar panels on Earth, allowing them to generate more electricity. Conversely, during quieter phases of the cycle, solar radiation decreases. This subtle ebb and flow of energy output affects how much electricity can be harnessed from sunlight in any given period. The relationship between the solar cycle and solar radiation is a delicate balance, reflecting the natural rhythms of the universe. As the sun continues its journey through this cycle, solar panels quietly adjust to the changing levels of light and heat. They absorb the sun's energy, transforming it into usable power. This continuous interaction between the sun's activity and the materials on Earth, unfolding over time, embodies a sense of harmony. Each moment in this cycle passes, contributing to a greater understanding of the gentle forces at play. In certain materials known as superconductors, electricity flows effortlessly, unimpeded by resistance. This means that when these materials are cooled below a specific temperature, often referred to as the critical temperature, electrons can move freely. They glide along paths created within the structure of the material, encountering no barriers, no friction to slow them down. This remarkable property allows an electric current to persist indefinitely in these superconductors, creating a smooth, continuous flow. The journey of electricity within them becomes tranquil, like a whisper moving through the quiet night air. These materials showcase how, under the right conditions, fundamental forces can converge in harmony, allowing energy to circulate endlessly without loss. As the temperature remains low, the stable environment encourages this uninterrupted movement, reflecting the intricate dance of atoms and electrons working together seamlessly. It is a gentle reminder of the wonders of the natural world, where balance and order create a serene flow of energy, ready to sustain itself quietly in the depths of the universe. In electrical components, resistance is not always a constant feature. Over time, it may shift gently and gradually, influenced by various factors within the environment. Temperature changes can play a subtle role, as heat may cause the materials to expand or contract, impacting how easily electricity can flow through. Similarly, humidity can interact with these materials, introducing moisture that may lead to gradual wear or degradation. This delicate interplay means that the energy conducted through a circuit can decrease as resistance gradually increases. When resistance rises, less current can pass through, reducing the overall efficiency of the system. The once vibrant flow of electricity can soften, making the movement feel slower and more restrained. Quietly, these changes occur, often unnoticed, but they remind us of the ever-evolving nature of physical systems. The intricate relationships among temperature, humidity, and resistance create a dynamic and constantly shifting landscape within electrical components, reflecting the gentle transition of time itself. Everything continues to flow, awaiting the next moment in a tranquil procession of energy. Electromagnetic waves generated by electricity exist as a gentle ripple through the environment. These waves travel gracefully, mingling with the molecules in the atmosphere. As they move, they interact in delicate ways, shaping their journey through the air. This interaction can influence the clarity and strength of the signals carried by these waves as they encounter various atmospheric conditions. The presence of moisture, temperature variations, or even particles suspended in the air can play a subtle role in how these waves propagate. Over time, these factors may cause shifts in signal quality, leading to a gentle ebb and flow in clarity and distance. Disturbances in the atmosphere can obscure their path, causing changes that might not be immediately noticeable, but nonetheless affect their reliability. This continuous dance of waves and molecules unfolds quietly, influencing the way information travels across distances. As electromagnetic waves weave through the air, they engage with their surroundings, adapting and transforming in an ongoing process that reflects the dynamic nature of the world around us. Each moment brings possibilities as the waves continue on their unseen paths, ready for what lies ahead. Wiring in homes is arranged with care, creating a network that guides electricity throughout. This layout flows through walls and ceilings, extending from the main source like a quiet stream of energy, reaching into different rooms. The careful placement of wires ensures a steady path, allowing electricity to travel efficiently and consistently. As time passes, this arrangement remains stable, untouched by the changing environment around it. The wiring, safely encased, holds its structure, providing an unchanging avenue for energy to flow. There is a calm reliability in this consistent access to electricity, a quiet assurance that the connection remains intact, day after day, year after year. Each wire serves its purpose, leading energy to lights, outlets, and appliances without interruption. The gentle hum of electricity dances silently within the walls, a continuous presence that supports the daily workings of the home. In this harmonious arrangement, the journey of electricity continues, ever ready to reach its destination, patiently awaiting the moment it is called upon once again. Electric fields, emerging from the presence of charges, quietly shape the behavior of particles within their reach. These fields create influences that can guide the motion of charged particles, even under the pull of gravity. In the atmosphere, such a subtle interaction occurs as electric fields weave through the air, affecting the path of ions suspended in the sky. As the particles drift within these fields, they may gain energy, moving with an increasing velocity. When conditions align, this acceleration contributes to the formation of lightning during storms, where the powerful discharge of energy forms a visual spectacle. The interactions between electric fields and particles are constant, albeit invisible. Ions sway within the embrace of these fields, dancing to an unseen rhythm, a ballet of charges that continues as long as the conditions persist. The atmosphere hums softly, charged with possibility, a place where forces linger, forever available to shape the pathways of particles drifting through the calm expanse above. The Earth's magnetic field, a vast and gentle force, steadily shifts over long periods. This magnetic fabric originates deep within the planet, where molten iron flows, generating fields that stretch out into space. These changes occur slowly, often unnoticed day by day, yet over centuries they accumulate, subtly transforming the landscape of the magnetic field. As the core's movements influence the field, alterations can affect various electrical systems nestled in our atmosphere and on the surface. Satellites, those silent watchers, rely on the stability of this magnetic presence to navigate and communicate with precision. Any undulations in the magnetic field can gently shift their operational paths, softly nudging them as they orbit above. Navigation systems, those delicate constructs that map our journeys, are guided by the same magnetic flow. When the Earth's magnetic field changes, these systems adapt, responding to its silent whispers. This connection infuses the environment with a quiet dynamism, a dance of forces operating in harmony, ready to guide the particles and currents that traverse our planet's embrace. Electric fields, the invisible forces at play in the world around us, offer a glimpse into the behavior of charged particles. As one moves further from the source of these fields, the strength of the force experienced by other charged particles gently diminishes. This soft decline in strength is predictable and consistent, forming a serene pattern that can be understood through the inverse square law. In this delicate balance, as the distance increases, the influence of the electric field diminishes with the square of that distance. A calming consistency emerges, allowing for a gentle interaction between charged entities. The strength of the electric field may feel powerful close to its source, but as one drifts away, it gracefully fades, like a whisper dissipating into the air. This natural reduction fosters a quiet harmony in the environment, influencing the behaviors of particles as they navigate their space. Each field, in its declining influence, provides a soft foundation for the movement and interaction of electric charges, allowing the universe to unfold in a steady, understated manner, always ready to share its secrets in the stillness of the night. At the heart of the electromagnetic spectrum lies a range of frequencies that define the behavior of electricity. This spectrum acts as a quiet boundary, guiding the flow and function of electric currents. Within this realm, certain frequencies shine bright, supporting the efficient movement of energy through circuits. However, as frequencies ascend beyond this optimal range, a gentle shift occurs. Higher frequencies can lead to challenges that introduce energy loss. As the waves move faster and become more complex, the circuits may struggle to maintain efficiency. This delicate balance underscores how the structure of the electromagnetic spectrum influences the way electricity behaves. As frequencies rise, the simplicity of flow begins to waver, resulting in energy that may not travel as seamlessly through a circuit. The interplay between frequency and efficiency creates a natural limit, gently reminding us of the harmony required for smooth energy transfer. Embracing this flow invites a sense of calm, as systems operate best within their defined ranges, softly enhancing the rhythm of electric currents. Throughout the day, electrical grids hum in a rhythm that mirrors the natural patterns of life. Each cycle is marked by gentle fluctuations in demand, driven by the movements and routines of countless systems. As the afternoon deepens and the world transitions into evening, the demand on these grids gradually rises. This peak demand often unfolds as more people return home, bringing with them the familiar requests for light, warmth, and comfort. During this time, electricity flows more densely, as if embracing the surroundings. The infrastructure responds to this surge, channeling energy eagerly through networks of transmission lines. With great care, each component of the grid interacts seamlessly, allowing for a responsive dance of energy. These daily cycles reflect a deep connection to human rhythms, although they exist quietly beneath the surface. As evening settles in, demand may stabilize or gently decline as activities shift and homes become quieter spaces. The grid, having withstood the daily ebb and flow, rests in a state of readiness, fully prepared to meet the needs that await with the dawn. This calming cycle continues, whispering a promise of balance in the dance of energy, ensuring that a soft and steady current awaits every moment. Within the confines of a battery, a delicate interplay of chemicals occurs, unfolding quietly as electricity is released. These chemicals, carefully selected for their properties, engage in reactions that generate electrical energy. During this process, subtle transformations take place. They change state from one form to another, releasing energy in a consistent, steady manner. Over time, these same chemicals can slowly begin to break down. This gradual change does not happen all at once, but rather unfolds over extended periods. As degradation occurs, it affects the overall performance of the battery. The once efficient and responsive reactions may become slower, leading to diminished energy output. As the chemistry evolves, the battery reaches a state of equilibrium where its ability to deliver power smooths out. This gentle transition reflects the natural life cycle of the chemicals within. Each phase carries its own rhythm, contributing to the quiet life cycle of the battery. In this way, the enduring yet subtle changes within the battery resonate with the continuous flow of energy, ready to enter a new cycle when needed. In certain materials, a remarkable phenomenon occurs when they are cooled to extremely low temperatures. This condition allows these materials to enter a state known as superconductivity. In this state, they can conduct electricity effortlessly, without any resistance. It is a unique behavior that contrasts sharply with most substances, where resistance is a natural characteristic that generates heat and dissipates energy during electrical flow. Superconductivity is found in only a select few materials, and these varying substances respond differently to the cold. As they reach these low temperatures, the lattice structure of the materials becomes stable, allowing the electrons to move freely. In essence, the usual obstacles that hinder electrical conduction simply vanish. The seamless flow of electricity continues without loss, creating a perfect circuit within the material. The results of this phenomenon can be both fascinating and useful, as they pave the way for deeper understanding in the field of physics. The quiet dance of electrons within these superconductors, engaging in their own rhythm, maintains a state of balance, yet opens the door to new potential. Each cool moment spent in this state unfolds gently, ready to return to its original form when conditions change again. When energy storage technologies develop, they begin to reshape the dynamics of electricity usage. These advancements allow for more effective containment of electrical energy, enabling it to be saved for later. This efficiency leads to the establishment of long-term cycles that can influence both pricing and demand in subtle ways. With improved energy storage, electricity can be collected at times of low demand, often when production exceeds consumption. During these moments, electricity can be stored, waiting patiently for when it is needed most. As peaks in demand occur, the stored energy can be released, helping to stabilize supply fluctuations that are common in electrical grids. Over time, these natural cycles reflect the ebb and flow of energy needs, contributing to a balance that is beneficial for the overall system. It allows for a smoother integration of various energy sources and contributes to a greater harmony within the network. Each cycle unfolds with its own rhythm, hinting at a world that adapts and evolves, continuously shaping itself over time. Within electrical wires, a core made of metal serves as the primary conduit for electric current. This metal, commonly copper or aluminum, possesses properties that allow it to efficiently transport electrical energy. As the current flows through this conductive core, a seamless journey unfolds, with electrons moving steadily through the material. Surrounding this core lies a layer of insulation, often made of rubber or plastic. This protective covering plays a vital role, ensuring that the electric current remains contained within the metal core. It acts as a barrier, reducing the risk of accidental shocks and safeguarding against interference from external elements. The insulation is carefully designed to withstand a range of environmental conditions, maintaining its integrity over time. The combination of the conductive core and the insulating layer creates a delicate balance within each wire, facilitating the smooth movement of electricity while ensuring safety. Together, they form a quiet unity, allowing energy to flow with purpose and precision. As these elements exist in harmony, they support an intricate web of connections, ever ready to channel power when needed. Electrical grids possess a remarkable ability to evolve over time. Initially, they often function as centralized systems, with large power plants generating electricity that is then transmitted over long distances to reach consumers. This method creates a vast network where energy flows from a few major sources to many endpoints. As years go by, a subtle shift begins to occur. Local energy sources, such as solar panels, gradually make their presence felt. These individual systems can harness energy right where it is needed, enabling a more decentralized approach to electricity. As more homes and buildings adopt these technologies, the dynamic of energy distribution begins to change. The electricity generated locally can be utilized immediately, reducing the dependence on far-off generation stations. This transition fosters a diverse energy landscape that allows for greater resilience. The grid becomes more intricate, yet beautifully interconnected, with the potential for energy to move more freely among a multitude of sources. The interplay between centralized and decentralized systems unfolds slowly, revealing a landscape brimming with possibilities. The development of this energy web hints at a future where power flows gently through many avenues, nurturing a serene balance within the grid. The Earth's crust, a vast and ever-changing layer that encases our planet, undergoes slow movements across millions of years. These shifts occur as tectonic plates glide over a semi-fluid layer beneath them, creating a subtle dance of geological forces. Over great expanses of time, these slow movements can affect the landscape significantly, altering everything from mountain ranges to valleys. Power lines, which traverse this dynamic surface, may find themselves in new positions as the land gradually transforms. Routes that were once optimal for electricity distribution may change, leading to an evolution in how energy flows across various regions. With the gradual shifting of the crust, natural features can redirect the pathways of these power lines. This process contributes to a complex network of distribution, one that adapts alongside the landscape it traverses. As the Earth's surface evolves, so too does the intricate system of energy management. These changes unfold gently, reflecting the quiet yet powerful forces at work beneath our feet. The interaction between the crust's movements and the electric grid creates a continuous, flowing relationship as both systems adapt in serene harmony. Electricity, when stored in a confined space, exhibits a specific energy density that provides insight into how much energy can be contained within a particular volume. For lithium-ion batteries, this energy density is measured at around 3.6 megajoules per liter. This value reflects a balance of chemical composition and physical structure, enabling these batteries to hold substantial energy in a relatively small package. Under normal conditions, this energy density remains fairly stable, allowing for consistent performance over time. However, Subtle changes can occur as temperatures fluctuate or as the battery undergoes regular charge and discharge cycles. Over time, as the battery ages, its energy density may gradually shift, reflecting the complex interactions of its internal chemistry. Such behaviors symbolize the delicate equilibrium within the battery, highlighting how it responds gently to environmental factors. Like many natural systems, this storage of energy remains in a state of quiet adaptation, maintaining an ongoing relationship with its surroundings. The energy contained within continues to embody a calm potential, ready to be released when needed. As the cycles of charge and discharge unfold, the battery exists as a steady presence, quietly holding its energy within the confines of its structure. Static electricity reveals itself through subtle interactions between charged objects and their surroundings. When a balloon is rubbed against a surface, it becomes charged, accumulating an excess of electric charge. This process creates an invisible force around the balloon. As it approaches small, lightweight objects, the electric charges begin to interact with the atoms in those materials. The attraction arises from the imbalances of electrical forces, pulling tiny particles closer to the balloon. This phenomenon demonstrates how electric charges can influence one another at a distance, even without direct contact. The charged balloon can draw paper scraps or strands of hair toward itself, creating a gentle dance of movement. These small objects, once still, become animated as discrete electric forces work to rearrange their position. The behavior of static electricity is a reminder of the delicate balance of forces at play in our environment. These interactions, though often subtle and quiet, illustrate the continual movement of energy around us. The phenomenon's simplicity holds a certain calmness, revealing how nature can create tiny moments of wonder through the fundamental principles of electric charge. In this silent exchange, the world around us resonates with gentle currents, waiting to express its quiet energy. Capacitance embodies the capacity of a system to hold and store electric charge. Within this framework, a capacitor serves as a key component, designed to gather energy in the form of an electric field. When a voltage is applied, the capacitor collects charge on its plates, creating an internal environment that balances positive and negative charges. The stored energy rests quietly, waiting for the right moment to be released. This release can occur gently and steadily, allowing the capacitor to provide a smooth flow of energy. As the stored charge is drawn from the capacitor, it moves through a circuit, contributing to the flow of electricity. This regulated release of energy plays a significant role in enhancing the efficiency of many systems, guiding the electric current in a controlled manner. The behavior of capacitance demonstrates how energy can be conserved and utilized with care. It invites a sense of balance within electrical systems, fostering calm and stable energy distributions. This quiet process of storing and releasing energy continues, whispering of the interconnectedness of charge and flow, remaining poised for whenever the moment calls for it. Electric potential energy is a form of energy linked to the position of charged particles within an electric field. It embodies the capacity of a system to release energy based on the arrangement and strength of this field. When the influences of distance and strength remain fairly constant, the electric potential energy preserves its stability. This balance allows for a serene continuation of energy storage. In systems like capacitors, this stable potential energy plays a vital role. The electric field within the capacitor retains energy effectively, holding it in a gentle embrace until called upon for discharge. Under unchanging conditions, the energy remains quietly poised, creating a harmonious internal atmosphere. Such stability ensures that energy can be relied upon when needed, framing a constant backdrop for the eventual flow of electric current. The calmness of the electric field reflects a peaceful coexistence of charges, waiting patiently to release their potential when the moment is right. This serene readiness of energy, resting in its potential form, offers a glimpse into the tranquility of electric systems, where everything exists in a delicate balance, poised for continuity. Electrical resistance is a property intrinsic to materials that conduct electricity. It determines how much a material opposes the flow of electric current. One significant factor influencing this resistance is temperature. As the temperature of a conductor increases, its electrical resistance also rises. This relationship creates a quiet interplay within the material's structure. When the temperature climbs, the atoms in the conductor vibrate more vigorously. This movement interferes with the passage of electrons, making it more difficult for them to flow smoothly. This increased resistance can lead to energy being lost in the form of heat. The gentle warmth radiating from the conductor is a byproduct of this resistance. Over time, these energy losses can accumulate, subtly affecting the overall efficiency of the system. In this delicate balance, the electrical energy is transformed into thermal energy, gently reminding us of the interconnectedness within these materials. As time passes, this quiet transformation continues, maintaining an ongoing relationship between temperature and resistance, each influencing the other in a soft rhythm. The flow of energy, while impacted, persists in its quiet journey, showcasing the natural dance of electricity and heat. Electric arcs are fascinating manifestations of electricity that arise under particular circumstances. When a sufficient voltage is applied across a gap between conductive materials, air can become ionized, allowing a continuous flow of electric current. This ionization transforms the surrounding air into a conductive path, enabling the arc to persist. This beautiful phenomenon creates a glowing arc of light that can be both illuminating and mesmerizing. The stability of an electric arc depends on various factors. The distance between the electrodes plays a crucial role, as does the material used. These arcs can fluctuate in brightness and form, yet they establish a consistent flow of energy within their defined environment. As long as the conditions remain favorable, sufficient voltage and a conducive atmosphere, the arc continues to burn, illuminating a small space with its soft glow. While mesmerizing, electric arcs also embody a fascinating aspect of electrical behavior, quietly reminding us of the intricate dance of charged particles in motion. As the arc persists, it illustrates a delicate balance of forces at play, a gentle flow of energy that finds stability even in the dynamic realm of electricity. Power plants represent a complex interplay of natural resources and mechanical systems, dedicated to generating electricity over extended periods. Within these facilities, various fuel sources play a crucial role in ensuring consistent energy output. Coal, a dense and energy-rich material, undergoes combustion in large furnaces, releasing heat that transforms water into steam. This steam then drives turbines, converting thermal energy into electrical energy. Nuclear energy, on the other hand, relies on the process of nuclear fission, where atomic nuclei split to release substantial amounts of energy. This process also generates heat, which is utilized similarly to the coal method, producing steam to drive turbines. Both systems can maintain a steady flow of electricity as long as their resources remain intact and properly managed. The infrastructure is designed to maximize efficiency, allowing a continuous cycle of energy production. The rhythm of electricity generation ebbs and flows, responding to the availability of fuel. Yet, in the heart of the power plant, the mechanisms continue to work in unison, quietly providing energy as long as conditions allow. In certain atmospheric conditions, electricity takes on a fascinating form known as ball lightning. This phenomenon can appear during thunderstorms, characterized by luminous spheres that float and dance through the air. These glowing orbs vary in size and color, often casting a soft, warm glow against the darkened sky. Ball lightning typically lasts only a few seconds, existing in a delicate balance of energy and matter. Researchers believe it may be related to the discharge of electricity in the atmosphere, possibly linked to the ionization of air molecules. This process creates a unique environment where these radiant spheres can manifest momentarily. The behavior of ball lightning often seems erratic, moving in unpredictable directions before fading away. Despite being reported across different cultures and locations, the exact physical properties of ball lightning remain elusive. Each sighting adds to the mystery surrounding this rare manifestation of electrical energy. In these quiet moments, the transient beauty of ball lightning emerges, inviting wonder and curiosity, floating softly within the natural world. Improvements in energy efficiency occur gradually, marked by steady advancements in technology. Over time, appliances are designed to use less electricity while still delivering the same level of performance. These enhancements often arise from new materials, better engineering, and refined manufacturing processes that prioritize conservation. With each new generation of appliances, features become more sophisticated, yet simpler in their consumption of energy. For instance, motors may become more efficient, and insulations improve, allowing refrigerators or washing machines to operate less while maintaining effectiveness. This quiet transition leads to a noticeable decrease in overall electricity consumption across households. As energy efficiency grows, so does the potential for a collective reduction in energy demand. Households can maintain comfort and convenience without straining resources. This gradual evolution reflects a silent shift in how energy is used, creating a harmonious balance between necessity and conservation, allowing each home to step gently towards a more sustainable way of living. In these moments, the rhythm of technology continues, softly ushering in change while blending seamlessly into daily life. Electricity moves through a circuit in a steady, unbroken path. When the power source is stable, this flow can be like a gentle stream, providing energy to devices that require it. A battery with its stored energy can release electricity in a controlled manner. Similarly, a generator creates a consistent flow, transforming mechanical energy into electrical energy without interruption. As long as the source remains reliable, this flow allows devices to operate smoothly, whether it is the soft hum of a lamp illuminating a room or the quiet efficiency of an appliance. Each component thrives on the steady supply of electricity. This reliable current powers the intricate mechanisms within, enabling them to function seamlessly over extended periods. With this continuous flow, energy can travel through wires, connecting various elements of a system. Each circuit, with its unique pathways and components, contributes to the larger tapestry of energy distribution. It unfolds quietly, creating a framework that supports consistent performance, ready to carry on with its silent work. Each moment, the potential for energy remains, allowing for calm, steady operation, inviting thoughts to drift softly along with the rhythm of this quiet dance of electrons. Electricity generation moves through an evolutionary process, gradually evolving as technologies emerge and improve. In many regions, The reliance on coal as a primary source of power has shifted slowly towards cleaner options, such as wind and solar energy. This transition does not occur overnight. It unfolds over years, reflecting careful planning and sustained effort. The landscape of energy production is transformed in subtle ways. New structures, such as solar farms or wind turbines, are integrated into the environment step by step. Each new installation requires thoughtful consideration, reflecting advancements in engineering and materials. Investment is essential in this transformation, fostering the development of new technologies that can capture and convert natural energy. Over time, these changes become part of a larger picture, where power generation aligns more closely with the cycles of nature. With each evolution, the systems deepen their roots, creating a more resilient energy supply. The gentle flow of these advancements lingers in the background, harmonizing with the needs of the present while holding space for the future. The quiet movement towards renewables continues, an ongoing reflection of possibilities yet to be realized. Power plants, like many complex systems, undergo gradual changes over time. As the equipment within ages, it can become less efficient, quietly affecting the output of energy. Components may show signs of wear, leading to subtle shifts in performance that can go unnoticed until they accumulate. This slow decline in efficiency can manifest as an increase in emissions, reflecting the age of the machinery and the limitations of older technologies. The interplay of age and advancements in engineering creates a landscape where older systems struggle to keep pace with newer, cleaner technologies. Reliability can also wane, with fluctuations in energy output that mirror the state of the equipment. As parts of the power plant function with diminished capability, the overall harmony of energy production may be disrupted. Each passing year brings the potential for change, and as these shifts quietly unfold, they signal a need for renewal. Emissions rise and fall like a soft tide, reminding us that systems, no matter how sturdy, are in a constant state of evolution. In this dance of time and technology, the gentle urge for improvement lingers softly in the background, waiting to find its place in the ongoing rhythm of energy generation. Inside power plants, generators play a vital role in transforming mechanical energy into electrical energy. At the heart of this process, coils of wire and magnets work in quiet harmony. The arrangement of these components creates a continual interaction between magnetic fields and electric currents, a phenomenon that is both elegantly simple and profoundly effective. As the mechanical energy moves through the system, it causes the coils to spin within the magnetic field. This motion generates electric currents, aligning them with the principles of electromagnetic induction. This relationship is steady and reliable, allowing energy to flow in a defined manner, reflecting the natural laws at play. Every movement, however subtle, contributes to the overall functionality of the generator, revealing the intricate balance of forces. The magnetic fields hold a timeless quality as they guide the currents along their path. This gentle interplay, while complex, maintains an enduring rhythm, fostering a continuous production of energy. Each moment adds to the ongoing cycle, inviting a sense of connection with the deeper mechanisms of nature. Within this setup, there lies a calm assurance, a steady heartbeat that mirrors the pulse of electricity itself, ready to unfold further into the night. Over time, electrical devices experience a gradual shift in their reliability. Each tiny operation, like a heartbeat, contributes to a gentle wear and tear on their internal components. Among these, capacitors play a significant role. These small, seemingly simple parts hold and release energy, helping to stabilize the flow within the device. As they age, they may become less capable of performing their function. This slow decline can lead to a gradual loss of functionality, where what was once seamless may begin to falter. It is a quiet process, often unnoticed in the day-to-day, yet it reflects the delicate balance of energy and time. With every cycle of energy passing through, the materials, like metals and plastics, undergo subtle changes. These shifts can lead to small inefficiencies, affecting the overall system. Such internal transformations are a reminder of the finite nature of all things, even those that seem designed to endure. The mechanism continues to function, albeit with diminishing returns, embodying the passage of time in its own steady way. In this intricate dance of energy, there remains a persistence, an ongoing rhythm, ready to guide the next moment into being. Over the years, the materials used for electricity transmission, like copper and aluminum wires, undergo a gradual change. As they age, these conductors can lose some of their efficiency. The flow of electricity through these aging wires may encounter subtle resistances, causing energy to dissipate in forms such as heat. This slow degradation often goes unnoticed, yet it is a silent reminder of the passage of time within the system. As the years unfold, the integrity of these materials may weaken. Factors like temperature fluctuations and environmental conditions contribute to this gradual decline, creating changes at the molecular level. The characteristics of the wire can shift, leading to diminishing performance as energy flows through. Utilities, in their quiet vigilance, may monitor these systems, selecting moments to replace and renew the materials to maintain optimal functioning. This careful replenishment reveals a commitment to sustaining the delicate balance of energy flow, allowing the system to continue its role in the ever-evolving tapestry of electricity. In this ongoing process, the wires whisper the story of endurance and transformation, remaining ready for the next pulse of energy as time moves gently onward. Electricity travels through grids that have been designed to carry energy over extensive distances. These grids consist of a network of transmission lines and substations, expertly organized to facilitate the movement of power from generation sites to far-reaching destinations. The materials within these lines are chosen for their ability to conduct electricity efficiently, minimizing losses as the energy flows. Over time, these systems have been meticulously maintained. With each passing year, their resilience has allowed for a stable distribution of power across large areas. Despite the vast stretches of landscape they cover, the design helps ensure that significant losses remain minimal. This efficiency allows communities, towns, and cities to draw from a shared source of energy, connecting diverse regions seamlessly. The internal structure of the grid implies a delicate balance, where various components work in harmony to support the flow of electricity. Notably, this connectivity enhances the reliability of power delivery, standing the test of time while adapting to the subtle shifts in demand. Through these gentle currents, the grid continues to weave its quiet web, ready to support every flicker of light and hum of energy as the night deepens peacefully around it. The stability of electric power systems is a delicate harmony between supply and demand. Electricity flows continuously, creating a dynamic balance that must be maintained for the system to function smoothly. When power generation aligns closely with the energy that is drawn from the grid, everything operates in a tranquil rhythm. Each component, from generators to transmission lines, is designed to support this balance. If there is an excess of electricity produced without sufficient demand, the system may become unstable. This excess can cause variations in frequency, which can ultimately lead to disruptions. Such fluctuations might result in outages, gentle reminders of the intricate interconnectedness of the power grid. On the other hand, when demand rises and outstrips the available supply, the grid must adapt quickly to restore equilibrium. Power plants can respond to these shifts, modifying their output to match the consumption patterns observed across the network. This ongoing adjustment is crucial for maintaining continuity, allowing for a calm distribution of energy. As the night carries on, the smooth functioning of these electric systems persists quietly, ready to shift seamlessly between the ebb and flow of needs, like a constant, reassuring pulse in the darkness. Capacitors function as quiet reservoirs of electrical energy. These components have the ability to store energy within an electric field, allowing them to hold a charge for considerable durations. This stored energy can then be released slowly, creating a steady and reliable output. The internal structure of a capacitor consists of two conductive plates separated by an insulating material or dielectric, which helps to manage how energy is absorbed and dispensed. As the capacitor charges, energy accumulates within, creating a balanced state. When the energy is needed, the capacitor discharges. This transition is smooth and controlled, allowing for a stable release of power over time. This gradual process can be essential in maintaining harmony within larger systems where sudden fluctuations might disrupt the balance. As energy flows in and out, the capacitor helps to stabilize voltage and ensure consistent performance. This capability plays a crucial role in enhancing the overall reliability of electric systems. Each charge and discharge is a calm exchange, contributing to a seamless network, always poised to provide energy as needed, like a gentle tide ready to flow. Electricity is composed of tiny particles known as electrons. These electrons are remarkable in their ability to move through various materials. In certain substances, such as copper, electrons can flow with ease. This smooth movement allows for the efficient transfer of electrical energy from one place to another. Within a copper wire, countless electrons drift and glide, creating a current that carries energy through the material. The structure of conductors like copper encourages this free movement. The arrangement of atoms creates pathways that allow electrons to navigate without obstruction. In contrast, other materials may inhibit the flow of these particles, resulting in higher resistance. This natural variance among substances shapes the behavior of electricity in different contexts. As electrons travel, they create a gentle rhythm, much like a steady stream, moving through an intricate network of connections. Each electron contributes to the overall flow, bringing energy where it is needed, always in a calm and continuous manner. The dance of these particles is a fundamental part of the unseen world around us, quietly underpinning the flow of electricity. The temperature at which a superconductor enters its superconducting state is a fascinating aspect of its nature. This critical temperature is often quite low, typically falling below -200 degrees Celsius for conventional superconductors. Within this chilled environment, the material undergoes a remarkable transformation. At such low temperatures, the atomic structure of the superconductor allows electrons to pair up, forming what are known as Cooper pairs. This pairing minimizes resistance, enabling electrons to move freely without losing energy. Interestingly, this critical temperature remains constant under steady-state conditions, providing a stable threshold for the material's superconducting behavior. Even as researchers strive for breakthroughs, the quest for superconductors that can operate at higher temperatures continues, offering the promise of diverse exploration within this field. The interplay of temperature and electron dynamics adds layers to our understanding, revealing a world where matter behaves in unique and unexpected ways. The gentle balance of conditions needed for superconductivity fosters an atmosphere of anticipation, where each discovery leads closer to the potential of new phenomena waiting to be unveiled. Certain trees exhibit a fascinating phenomenon known as electricity from sap. In this quiet process, the movement of sap through the tree can generate small electrical charges. Sap, which flows through the vascular system of the tree, is rich in water and various solutes. As the sap travels, it encounters changes in pressure and flow dynamics. These movements can create conditions that allow for the separation of charges, leading to the generation of minute electrical fields. This interaction with electrical forces reveals a subtle connection between biological systems and electricity, showcasing how living organisms can engage with the physical laws that govern the natural world. The gentle flow of sap mirrors the soft currents of energy that traverse the tree, creating a serene harmony between life and the invisible forces at play. As we explore this quiet realm, the whispers of electricity flow through the trunks and branches, highlighting a dynamic interplay that unfolds over time, ever ready to be observed further, like a tranquil stream flowing through a peaceful forest. Gravity plays a subtle yet significant role in the flow of electricity within liquid conductors, such as molten metals during electrolysis. In this process, electricity is passed through the liquid, prompting the movement of charged particles. The influence of gravity can be observed as it gently directs the flow of materials within the molten state. As the gravitational pull acts on the liquid, it encourages certain materials to settle or distribute unevenly across the surface. This distribution can affect how efficiently the electrolysis occurs, as the effectiveness of the electrical flow can depend on the arrangement of these materials. Over time, this gravitational influence may lead to variations in product yield, reminding us that even in a fluid state, the force of gravity silently guides the behavior of electric currents. The dance of charge and mass within this molten landscape unfolds quietly, demonstrating a harmonious interaction between fundamental forces. This intricate balance continues to work seamlessly, flowing gently like a whisper in the stillness of a nighttime sky, creating a serene backdrop for the ongoing natural processes. When certain materials are rubbed together, an interesting phenomenon occurs in what is known as triboelectric charging. This process unfolds quietly, as one material can either gain or lose electrons, resulting in an unexpected electric charge. For example, when plastic is combed through hair, it can collect electrons from the hair. As the comb moves along individual strands, the friction between the two surfaces can shift tiny electrical particles, leading to a delicate imbalance of charges. This causes the plastic to become negatively charged, while the hair, in turn, becomes positively charged. Consequently, when the comb is held near the hair again, the two oppositely charged surfaces attract each other softly. This gentle attraction can create a delightful surprise, as the comb seems to stick to the hair in a quiet, almost playful manner. In this intricate dance of electrons, the materials interact with a subtlety that reflects the natural world's own balance of forces. Each occurrence is a reminder of how simple actions can lead to fascinating results, functioning in harmony with the surrounding environment and quietly inviting curiosity as they continue to unfold softly and effortlessly. Insulative materials play a vital role in the behavior of electricity within various devices. These materials, found in appliances, create a barrier that effectively prevents unwanted electrical currents from escaping. A gentle layer of insulation surrounds wires and components, ensuring that electricity remains safely contained, allowing for smooth operation. The physical structure of insulative materials is uniquely designed, encompassing a variety of elements that can resist the flow of electric current. This resistance helps maintain safety over time, as maintaining a consistent barrier can protect both the appliance and those who use it. The durability of these materials is essential, as they are built to withstand the changes in temperature and fluctuations in humidity that appliances often encounter. With every little surge of electricity flowing through its paths, insulative materials provide a quiet assurance, contributing to a steady and reliable functioning system. Their presence calms the environment, ensuring an inviting safety that feels integral to the fabric of the appliance itself, allowing it to carry out its role in a peaceful manner. There is an inherent simplicity in the way these materials function, yet their importance is profound, creating an invisible shield that continues to support the devices quietly, always ready for the next gentle charge. Inductance is a fundamental aspect of electrical circuits, gently weaving a connection between the flow of current and the magnetic fields that arise from it. When electricity moves through a conductor, it generates a magnetic field around it, creating a quiet storehouse of energy within that space. This connection allows the circuit to harness energy in a soft, undulating manner. As the electrical current fluctuates, the stored energy in the magnetic field is released, creating a dynamic interplay between the current and its surrounding environment. This release can help maintain stability, as it smooths out sudden changes in current that might otherwise disrupt the flow. Such interactions enhance the overall functionality of the system, guiding the energy in a composed and rhythmic fashion. The internal structure of inductance demonstrates how energy can be both accumulated and released, providing a continual ebb and flow that is vital for quiet efficiency. This delicate balance contributes to the calm operation of electrical systems as they hum along smoothly, ever attuned to the subtle changes in current, ready to adapt and respond in tranquil harmony. The breakdown voltage serves as a defining limit for insulators, quietly marking the threshold at which they can no longer maintain their non-conductive state. Within these materials, an electric field develops as voltage is applied, creating a balance between stored energy and the capacity to resist current flow. As the voltage approaches this maximum level, the insulator remains stable, gently safeguarding the flow of electricity. When the electric field intensifies and surpasses this critical point, a transformation occurs. The insulator, once a barrier, begins to exhibit conductive properties, allowing current to flow through it. This change can happen almost seamlessly as the insulator gives way to the overwhelming force of electricity. In this moment, the internal structure of the insulator becomes transformed, leading to a state where it can no longer fulfill its role as a protector. These transitions illustrate a fascinating aspect of materials under stress, showcasing the delicate balance between stability and change. Such behavior, while rapid, is rooted in the fundamental properties of the insulator, unfolding in a soft and intricate manner. Each moment of voltage buildup brings the insulator closer to its limit, tapping into the deeper nature of electrical systems, forever poised between energy and resistance, ready to shift and respond to the flow around it. The resistance of materials is not a fixed characteristic. Instead, it fluctuates gently with changes in temperature over time. As warmth seeps into the material, its atoms and molecules begin to vibrate more energetically. This movement can create barriers for the flow of electric current, causing the resistance to increase. Similarly, when the temperature drops, the vibrations slow down, often allowing electricity to flow more freely. These shifts in resistance are subtle, yet significant, influencing how efficiently materials conduct electricity. In power lines, even the smallest changes can lead to energy loss, as heat is generated during transmission. This loss, though gradual, accumulates over time and underscores the dynamic nature of how materials behave in different thermal environments. The interplay of temperature and resistance illustrates the inherent complexity of materials, revealing that their ability to conduct electricity is not merely a fixed state, but an evolving property. Each day, as temperatures rise and fall, materials engage in this silent dialogue, their internal structures responding softly to the warmth around them, always adapting, always changing, maintaining a delicate balance. In superconductors, there exists a remarkable condition where electricity flows without encountering any resistance. This fascinating phenomenon unfolds only below a certain critical temperature. When the temperature is lowered to this delicate threshold, the internal structure of the material transforms, allowing it to conduct electricity in a state of perfect efficiency. Within this serene environment, the charged particles glide effortlessly, creating an unbroken flow of current. However, as the temperature gradually rises above this critical point, the material reverts to its conventional conductive behavior. The once seamless flow encounters resistance, mirroring the properties of more familiar conductors. In this state, the quiet beauty of superconductivity fades, and energy loss begins to occur, leading to a less efficient transmission of electricity. The tranquility of superconductors lies in this precise balance of temperature. Below the critical threshold, they create an unhindered path, an effortless highway for electrical currents. Above it, they return to a state where their unique qualities are muted, yet their potential remains, silently waiting for the right moment to shine once again. Transformers, intricate components designed to manage voltage levels, have a life that spans many years. As time gently passes, these devices can experience slow changes in their performance. The internal structure of a transformer relies on insulation materials, which play a vital role in keeping the electrical flow stable and safe. Over decades, these insulating materials can gradually degrade, their properties diminishing in a silent, almost imperceptible manner. As they age, the efficiency with which a transformer can manage voltage levels begins to wane. With every year that unfolds, tiny shifts occur within the material, altering the pathways through which energy flows. These changes are not abrupt, rather they are subtle, like a soft ripple in a still pond, expanding quietly outward. This gradual aging process paints a picture of quiet resilience as transformers continue their role amidst changing materials. They adapt, though not without the effects of time, losing a bit of their ability to handle electrical currents as efficiently as they once did. Such transformations serve as reminders of the passage of time within their sturdy structures, quietly preparing to embrace whatever comes next in their enduring journey. Electricity, a fundamental element in our world, travels at astonishing speeds, particularly in a vacuum, where it can reach nearly 299,792 kilometers per second. This remarkable speed is an idealized scenario, allowing for a sense of immediacy that we often associate with the flow of energy. Yet, once electricity enters a conductor, those speeds begin to shift gently. In typical materials, such as copper or aluminum, the movement of electrical current encounters resistance. This resistance acts like a soft barrier, slowing down the flow. As electricity navigates through these conductive paths, it experiences a change in its pace, influenced by the very structure of the material. The interactions between electrons and the atoms of the conductor create a delicate dance where energy is released as heat, consuming a small part of that rapid momentum. This downshifting of speed, while imperceptible on a moment-to-moment basis, is a reminder of the intricate nature of how electricity travels. Each microscopic interaction shapes the experience of electrical flow, leading to a gentle unfolding of energy through the world around us, quietly making its way while embracing the calm resistance of the materials it traverses. The journey of electricity, therefore, is not just about speed, but also about the rich tapestry of physical interactions that occur along the way. In certain renewable energy systems, such as solar panels, the process of generating electricity unfolds with impressive consistency over many years. These panels harness sunlight, transforming radiant energy into electrical energy through a delicate interaction between semiconductors. As sunlight strikes their surface, it excites electrons, allowing them to flow and create an electric current. This transformation occurs with remarkable efficiency, often continuing for decades with only a slight gradual decrease in performance. Over time, the panels endure various environmental conditions, from bright sunshine to gentle rain, yet their core functionality remains intact. Each day, they awaken to the sun's warmth, engaging in that tender exchange of energy, quietly contributing to the electrical needs of the surrounding environment. The architecture of these solar panels plays an essential role in their durability, as the materials are engineered to withstand the passing seasons. This steady resilience allows them to continually fulfill their purpose, offering a reliable source of energy for many years to come. The beauty lies in their simplicity, as they silently convert sunlight into electricity without a dramatic decline in their capacity to do so. Each moment, the process slowly unfolds, an enduring cycle of energy transformation, gently weaving into the fabric of time while nurturing the potential for countless tomorrows. Electromagnetic waves, with their gentle oscillations, carry energy across vast distances. These waves create a delicate interplay of electric and magnetic fields, which work in harmony to propel energy through space. As they travel, these waves can affect their surroundings, interacting with various materials in subtle ways. The internal forces that govern electromagnetic waves help to define their unique characteristics, such as wavelength and frequency. Each wave, resonating softly, carries not just energy, but information, allowing for a silent exchange of signals. These signals can travel through air, water, and other media, shaping the environment they move through, influencing the behavior of atoms and molecules along their path. As time progresses, the persistent presence of electromagnetic waves can lead to changes in systems nearby. The interplay of these waves with technology demonstrates a quiet consistency, as communication systems rely on this very energy to function smoothly. They transmit data with a gentle ease, illustrating how the behavior of electromagnetic waves can contribute to the flow of information, intertwining with the natural world around them. In this continuous dance of energy and information, the waves persist, creating an ongoing connection that emerges from the subtle yet profound forces at work. An enclosure crafted from conductive materials, known as a Faraday cage, creates a unique environment in which external static and electromagnetic fields simply cannot penetrate. This structure relies on the inherent properties of conductivity, allowing electric charges to redistribute along its surface. As they move, these charges create a protective barrier that absorbs and dissipates incoming energy, effectively shielding the interior from interference. The design of such a cage can vary, from simple mesh to solid forms, each ensuring a space where sensitive electronic components can rest undisturbed. Inside, the absence of external electromagnetic disturbances fosters a stable environment, contributing to the consistent performance of devices housed within. The materials interact softly with any incoming waves, reflecting them away rather than allowing them to disrupt. Over time, the presence of a Faraday cage can safeguard delicate systems against fluctuations in the electromagnetic field, maintaining a quiet sanctuary for their operation. This phenomenon remains a fascinating testament to the interactions of electrical forces, creating an oasis for technology amidst a sea of energy. In this calm space, the relationship between the cage and the field surrounding it unfolds quietly, offering an endless moment of stability. Aging infrastructure, which includes various components of electrical systems, gradually experiences wear and tear over many years. The materials that once provided reliable service may begin to degrade, leading to inconsistencies in performance and reliability. These changes tend to create cyclical patterns of outages and repairs. As parts of the system falter, they can disrupt the steady flow of electricity, causing interruptions that ripple through connected networks. Each outage prompts a response, often resulting in focused repairs designed to restore functionality. Over time, these repeated cycles of failure and restoration can affect the overall availability of electricity, leading to unpredictable fluctuations in how much power can be offered to meet demand. The behavior of the infrastructure reveals a delicate balance between natural deterioration and necessary upkeep. Each repair serves as a temporary solution, yet the underlying issues may remain unresolved, perpetuating a cycle that requires continuous attention. As these systems age, the effects of their condition are felt across wider networks, quietly influencing the harmony of electrical supply and demand. The ongoing interactions among these components create a rhythmic, almost gentle flow of energy through time, an ongoing narrative connecting the past and the future. Electric fields possess the unique ability to influence the behavior of light, a phenomenon known as the electro-optic effect. This intriguing interaction occurs when light waves pass through certain materials that are affected by electric fields. As the electric field changes, the path that light takes can also bend and shift in a subtle way. This bending occurs due to alterations in the refractive index of the material, which determines how light travels through it. As the electric field is applied, it rearranges the internal structure of the material, giving rise to distinct optical properties. These changes effectively alter the light's trajectory, creating different patterns and intensities that can be finely tuned. In devices designed to harness this effect, a consistent electric input provides ongoing control over light behavior. This allows for precise adjustments, where the output can be manipulated with care. Such capabilities are particularly valuable in the realm of optical technology, laying the groundwork for various innovations. As light interacts with electric fields in this manner, the possibilities extend further into the quiet complexities of physics, offering a glimpse into a world where energy and light dance together in flowing harmony. These mechanisms continue to unfold, creating an endless tapestry of interactions ready to be explored. Electricity has a fundamental relationship with heat, particularly when it moves through materials that resist its flow. This process, known as Joule heating, involves energy being converted into thermal energy as the electric current encounters resistance. As electrons travel through a resistive material, they collide with atoms within that material, transferring some of their energy. This energy transfer manifests as heat. Over time, the consistent generation of heat can influence the internal structure of these materials. The continuous exposure to elevated temperatures can lead to changes in their properties. Metals may soften or become brittle, while insulating materials can degrade and lose their effectiveness. This gradual degradation can result in failure, particularly in components like wires and resistors that are integral to circuits. The effects of joule heating remind us of the delicate balance within electrical systems. As heat is produced, materials respond, adjusting their characteristics over time, shaping the reliability of their performance. There lies a quiet complexity in this cycle, where energy flows seamlessly, intertwining with the physical properties of materials, suggesting the ongoing dance of electricity and heat. Each moment brings the potential for transformation, waiting to be explored further. Thermal energy produced from resistance within electrical components plays a significant role in their long-term behavior. As the current flows, it induces continuous heating, creating a cycle of warm and cool periods. This fluctuation in temperature can lead to changes in the materials that comprise these components. Repeated heating can cause materials to expand and contract. Over time, this physical movement alters the internal structure, potentially causing microscopic cracks or weaknesses to form. Metals may experience shifts in their crystalline structure, leading to increased brittleness or reduced conductivity. Similarly, insulators can lose their effectiveness, altering their ability to prevent unwanted energy loss. These transformations are gradual, unfolding slowly as electrical currents persist over time. The delicate dance of heat and cooling cycles builds a narrative of wear and change, intertwining the properties of materials with their performance. In this quiet interaction, the essence of thermal energy gently reminds us of the ongoing journey within electrical components, a journey that invites further contemplation. Electricity flows through materials depending on their conductivity, which defines how easily electric charges can move within them. Conductors, such as copper and aluminum, possess a structure that allows electrons to move freely. This movement creates a pathway for electric current, enabling it to travel with minimal resistance. The arrangement of atoms in these materials plays a crucial role, as they permit the flow of electricity to occur smoothly. In contrast, insulators like rubber are designed to inhibit this flow. The tight bonds between their atoms restrict the movement of electrons, creating a barrier that prevents electric current from passing through. This difference in structure illustrates how materials can be categorized based on their physical properties. Understanding conductivity reveals a quiet complexity within materials, a balance between freedom of movement and confinement. Each type of material holds its own intrinsic characteristics, shaping the way electricity behaves as it encounters different substances. The subtle interactions at this level invite contemplation as they establish the foundation of electrical effects we observe in the world around us. In the quiet realm of electricity and its flow, the unseen structures guiding the behavior of energy extend far beyond the materials themselves. Government policies and regulations play a subtle yet crucial role in shaping the landscape of electricity supply and consumption. These frameworks can establish long-term cycles, influencing how energy is generated, distributed, and utilized. Decisions made at various levels create patterns that can last for years. For instance, regulatory measures may encourage the development of certain energy sources while discouraging others. This cycle can lead to significant investments in infrastructure as resources are allocated to support specific energy technologies and practices. Over time, the shifts brought about by these policies create pathways that determine not only which forms of energy thrive, but also how they interact within the larger grid. Such dynamics weave an intricate tapestry of cause and effect, quietly determining the relationship between supply and demand. The ebb and flow of electricity consumption can mirror these decisions as changes ripple through the system. Each investment in technology and infrastructure reflects the ongoing dialogue between natural resources and regulatory frameworks, creating a serene yet complex balance within the world of energy. This peaceful interplay invites consideration, revealing the understated connections that shape the flow of electricity itself. Within the silent flow of electricity through a circuit, a gentle yet persistent internal pressure emerges, shaped by the energy coursing through. This pressure can lead to intricate breakdown phenomena, such as arcing, where electricity leaps across gaps, creating luminous channels of energy. While this process may initially seem subtle, it extends far beyond a momentary flicker. Over time, this gradual change can exert forces on the components of the circuit, leading to wear and tear. Each pulse of energy may introduce tiny shifts in materials, creating microfractures that accumulate, quietly threatening the integrity of the system. Such continuous strain, though often unnoticed in the moment, can weaken connections and disrupt the carefully balanced flow of electricity. As these breakdown phenomena progress, they signal a slow decline that can culminate in failure. This journey emphasizes the delicate balance of forces within a circuit, as the internal pressures intertwine with the very nature of electric energy. Each moment of activity softly shapes the future state of the circuit, inviting contemplation of the intricate relationships that govern the flow of energy and the lasting effects of time on its path. Within the world of electronic devices, printed circuit boards, or PCBs, serve a crucial role in holding various components together. These boards are crafted from layers of materials, each chosen for its specific properties, ensuring that they remain stable and resilient over time. The arrangement of these layers creates a harmonious structure, one that supports intricate pathways for electrical flow while maintaining its integrity through cycles of use. As currents travel across the surface of the board, the carefully designed layers work together, absorbing and distributing energy. This interplay fosters a quiet connection between the components, allowing them to function in unison. Over time, the materials within the PCB continue to sustain their form, providing a consistent platform for the delicate interactions of electricity, even as the energy pulses through. Leaving behind subtle changes, there is a remarkable endurance in the design. This stability invites reflection on the lasting presence of the board, which adapts yet safeguards its essential characteristics. Each layer, each connection, plays an important role in the steady rhythm of electronic life, seamlessly continuing the cycle of energy and function in a gentle embrace of both simplicity and complexity. Amidst the continuous hum of daily life, the demand for electricity grows steadily, reflecting the changing needs of an expanding population. This gradual increase shapes the landscape of energy production over decades. As more individuals and devices seek to harness electrical power, the systems designed to deliver this energy must evolve. The rise in demand can gently guide the development of new power plants, each one a testament to the desire for stability in energy supply. The underlying infrastructure, from transmission lines to substations, must also adapt to this growing need, ensuring that electricity flows smoothly and reliably. In this complex dance of supply and demand, careful planning becomes essential. Investments in technology and resources create pathways for the future, supporting both the burgeoning demands and the natural rhythms of existing systems. Over time, The balance between generation and consumption seeks a harmonious alignment, fostering a steady flow of energy through the networks that connect everything. Each step taken in this journey reflects the quiet resilience of our energy landscape, an ongoing process that continues to nurture the intricate web of modern life, quietly prepared for the future ahead. Within the realm of electricity, dielectric materials possess fascinating characteristics that allow them to store electrical energy. When placed within an electric field, these materials become charged, capturing energy in a gentle embrace. This ability to retain energy without immediate release is a defining feature, as it creates a stable environment for electrical systems. In the interplay of opposites, dielectrics stand apart, providing a barrier that separates charges while facilitating their gathering. Remarkably, they can hold this energy for a significant duration, allowing for a balance within circuits. This storage capacity becomes particularly important in capacitors, where the precise management of energy flow is essential. The internal structure of dielectric materials contributes to their effectiveness, often composed of materials like ceramics or polymers. Their unique properties offer various pathways for energy management, allowing efficient interactions with electric fields. In this constant state of equilibrium, dielectric materials quietly support the dynamic world of electricity, ensuring a reliable foundation for many processes. Their role, though sometimes unnoticed, remains integral to the seamless flow of energy, harmonizing with the rhythms of electrical systems accustomed to the ebb and flow of charge. Electricity has a remarkable ability to bring about change at a molecular level through a process known as electrolysis. When an electric current passes through a conducting solution, it can initiate the breakdown of chemical compounds with a careful precision. A familiar example of this process is the splitting of water, which consists of 2 hydrogen atoms and 1 oxygen atom. In this transformation, the electric current flows through the water, energizing its molecules. This energy facilitates the separation of hydrogen and oxygen, allowing them to emerge as distinct gases. Each gas moves toward an electrode, where it collects, revealing a tangible shift in the chemical structure of the water. The parameters surrounding electrolysis are carefully maintained, governing the efficiency of this reaction and the purity of the resulting gases. The gentle flow of electricity creates a controlled environment where interactions proceed harmoniously, reflecting the balance inherent in the natural world. In this quiet manner, electrolysis stands as a serene example of how electricity can alter matter, revealing subtle yet profound shifts within the fabric of chemical compounds. Each process unfolds in its own time, echoing the rhythmic and delicate nature of a world guided by fundamental principles. Renewable energy sources, such as wind and solar, are deeply connected to the rhythms of nature and the changing climate. They draw upon natural elements, harnessing the power of sunlight and the movement of air to generate energy. Over time, however, the output of these sources does not remain constant. Instead, it may ebb and flow in response to multi-year climatic cycles. For instance, variations in seasonal weather patterns can influence how much sunlight reaches solar panels or how consistently the wind blows in a given area. These cycles, influenced by larger climatic trends, reveal a dynamic interplay between the environment and energy production. Some years may bring abundant sunlight and strong winds, resulting in higher output, while other periods may lead to lower availability due to persistent cloud cover or calm days. Such fluctuations highlight the natural variability inherent in these energy systems. They remind us of the gentle balances found within the ecosystems that surround us. The continuous movement of air and the journey of sunlight are both constant and unpredictable, echoing the soothing hum of the natural world. In this way, renewable energy serves as a reflection of nature's rich tapestry, where every cycle adds to the harmony of existence, inviting us to appreciate the delicate dance of energy and environment. In specific types of chemical batteries, a remarkable process unfolds, characterized by reversible chemical reactions. This essential feature allows the batteries to cycle between charging and discharging phases in a harmonious manner. During the charging process, electrical energy is converted into stored chemical energy, creating a stable reservoir ready to be tapped into later. When energy is needed, the battery enters its discharging phase, and the stored chemical energy is transformed back into electrical energy. This seamless transition can happen repeatedly over the course of many years. The delicate balance of these reversible reactions is crucial, as it enables the battery to maintain its integrity and effectiveness over time. The materials within these batteries shift in detailed ways as they engage in these reactions. At an atomic level, bonds form and break, creating a rhythm of energy movement that promotes longevity. This ability to hold and release energy with consistency speaks to the remarkable stability of the battery's internal structure, which adapts with grace to the demands placed upon it. As the cycles repeat, they embody a quiet resilience, offering a dependable source of energy that endures through the passage of time, ever ready to fulfill its role in the flow of energy. The nature of electricity production interacts intricately with the environment, a relationship that unfolds over many centuries. As energy sources evolve, especially when moving away from fossil fuels, significant changes begin to emerge. Fossil fuels, while once a predominant source of energy, contribute to air pollution. Sulfur dioxide, nitrogen oxides, and particulate matter can enter the atmosphere, causing harm to air quality and, in turn, affecting the health of living beings and ecosystems. With a gradual shift to cleaner energy sources, such as solar, wind, and hydroelectric power, the landscape of air quality can begin to transform. Over time, as these methods reduce or eliminate emissions, the atmosphere enjoys a reprieve. The invisible particles that once filled the air diminish, leading to a breath of fresh air for communities and ecosystems alike. This transition fosters a slow but steady improvement in public health, as clearer air supports a healthier environment for all forms of life. Life cycles, both for plants and animals, might thrive in cleaner surroundings, creating a ripple effect throughout the ecosystem. With each passing year, the benefits compound, illustrating the long-term effects of thoughtful energy production. Nature appears to rejuvenate, and the atmosphere starts to heal, presenting a hopeful narrative that encourages further consideration of the delicate balance within our planet's systems. These changes, occurring gradually and naturally, weave into the continuous story of our planet's health, a soft reminder of the gentle rhythm of progress and renewal. As electric current moves through a conductor, it generates heat, a process known as Joule heating. This happens because the flowing electrons collide with the atoms in the material, transferring energy. As these collisions occur, the internal structure of the conductor begins to warm, leading to a subtle but important transformation. The increase in temperature can cause the individual atoms to vibrate more vigorously, creating a dynamic environment within the material. Over time, this added energy may lead to expansion, changing the dimensions of the conductor. This gentle alteration in size can affect the physical properties of the material, such as its electrical resistance. In some cases, as the temperature rises sufficiently, a material may even undergo a phase change, transitioning from solid to liquid. This shift can significantly alter how the material behaves within its environment, affecting its performance in prolonged scenarios. Such variations unfold quietly, illustrating the intricate connection between energy flow and material integrity. Through these subtle processes, the dynamic interplay of heat and structure unfolds over time, leading to a rich tapestry of behavior inherent in conductive materials. Each small change contributes to the ongoing story of energy and matter, creating a calm, continuous cycle that invites gentle reflection. Electrical discharges, such as lightning, offer a fascinating glimpse into the relationship between electricity and light. When a bolt of lightning forms, it is a rapid release of electrical energy. This powerful surge travels through the atmosphere, creating an impressive display that illuminates the night sky. The intense heat generated by this electrical event can reach temperatures hotter than the surface of the sun, causing the surrounding air to expand rapidly. This sudden expansion produces the rumbling sound of thunder, a gentle reminder of the energy involved. In its wake, this electrical discharge can also ignite fires, leading to small alterations in the landscape around it. The light produced by lightning is not just a fleeting moment, it marks a transformation of energy, momentarily brightening the dark. Over time, the impact of such discharges can be seen in the earth beneath. The intense heat can change soil composition, leaving lasting effects on the local environment. Each flash of light is a dance of energy, revealing the intricate connections that govern natural phenomena. This quiet interplay invites contemplation, offering a serene understanding of how forces in nature blend and flow, leaving a peaceful promise of continuity in the rhythm of the world around us. Urban development can subtly reshape the landscape of electricity distribution. As cities grow outward, suburban areas often emerge, leading to an increase in the demand for electricity in these newly populated regions. This shift in energy consumption requires a thoughtful adjustment in the way electricity is delivered. Local grids must adapt to meet the new needs, evolving to distribute power efficiently throughout the changing environment. Over time, energy supply strategies will realign, ensuring that each growing community has access to reliable electricity. The infrastructure that supports this invisible current begins to reflect the patterns of life taking place around it. Lines of power weave through neighborhoods, quietly adapting to changes, like the gentle flow of water adjusting to the contours of a stream bed. In this interplay, a dance of energy unfolds, where the natural growth of places necessitates a responsive electricity distribution system. Such adjustments occur gradually, creating a harmonious relationship between the landscape and the lifeblood of energy that courses through it, quietly lighting homes and powering dreams in a balance that continues to evolve. Electricity holds an intrinsic ability to generate magnetic fields, a subtle yet powerful interaction that unfolds in various contexts. The presence of these magnetic forces often counteracts gravity, creating intriguing effects. In certain systems, this relationship becomes particularly evident. Magnets create fields that extend into the space around them, forming an invisible barrier. In specialized forms of transport, like maglev trains, this phenomenon allows the trains to levitate above the tracks. By using the principle of magnetic repulsion, these trains mysteriously float, eliminating direct contact with the surface and significantly reducing friction. This unique state of floating provides a smoother operation and opens pathways for higher speeds. The calm interaction between electricity and magnetism reveals a glimpse into the underlying principles of motion. Within this realm, forces quietly balance and align, creating an efficient mode of travel that dances with the very fabric of physics. As the world of electricity continues its gentle hum, it weaves together connections that redefine movement, embracing an elegant transition between forces that guide the future of transportation. The economic cycle unfolds in phases, each characterized by distinct patterns of activity. During periods of growth, a gentle rise in industrial activity takes place. Factories hum softly with increased machinery operation, and systems come alive with the energy required to meet rising demands. This vibrant activity naturally leads to higher electricity consumption, creating a rhythm that mirrors the pulse of production. As industries expand, they require more power to fuel their operations. The interconnectedness of various sectors showcases a flow where energy use escalates in tandem with economic progress. Power plants work steadily, generating electricity to keep pace with this increased appetite for energy. The delicate balance of supply and demand shapes the landscape of electricity management, quietly guiding resources toward areas of need. This cycle moves in tandem with the ebb and flow of economic activity, creating a gentle dance of consumption and generation. Each phase connects seamlessly to the next, reflecting a broader narrative that unfolds beyond the surface, embracing a complex interplay of forces that governs energy in tranquility. The day quietly draws to a close, curling into the soft embrace of night. Each gentle breath invites a deepening calm, settling into the stillness that surrounds. Imagining the vast, serene expanse of the universe, the stars twinkle softly, inviting warmth into the quiet. Shadows stretch and fade, allowing a sense of peace to wash over everything. Rest comes naturally as the mind gently slows. With every exhale, thoughts glide effortlessly, drifting away into the background. The rhythm of nature whispers a lullaby, cradling the body in peaceful awareness. The world outside hushed, each sound an echo of tranquility. The air is cool and inviting, wrapping around like a soft blanket, offering comfort and ease. In this serene moment, the heart finds repose. Each quiet pulse marks the passage into a restful sanctuary. Eyes grow heavy, surrendering to a gentle stillness. Every delicate sigh draws the spirit deeper into calm. As all elements of the day gently blend into the hush of night, a soft farewell drifts through the air. There is warmth in this closing, a belief that rest is nurturing. Take this moment to embrace the gentle quiet, releasing all tensions and worries. Good night from Sleepy Science Facts.